Today, you're going to learn, you're going to answer this question. What is a kinematic stack? We're going to talk about kinematic stacks, and you're going to write them up in the assignment and everything. And we're going to talk about basically about drawing position and velocity graphs together. Okay, so let's dive right into it. Let's draw a position versus time graph. This is position, and this is time. And that's it. That's all I'm going to draw. Okay, look at this and tell me what's missing. What have I not drawn on here? What have I not put?
Labels.
Well, I put label. Oh, you know what I should do? We're supposed to put a title, position versus time. The reason you want to do that on the AP test, they want on every graph you draw, they want to see a title to it. So I'm going to require that now. But notice that there are no numbers on here, right? You notice there's no numbers? So we have a name for a graph like this that doesn't have any numbers on it. It's called a qualitative graph. Just means no numbers. Or sometimes there's some numbers on it, but most of the numbers aren't there. But that doesn't mean you don't know anything. There's information there about some object that's moving, right? What do you know? Do you know something about the starting position of this object? Yeah, it starts on the positive side of the origin, doesn't it? It's not starting at the origin. It's not starting on the negative side of the origin. It's not way far away. It's pretty close to the origin, but it's right there. Okay? And what is true about the velocity of the object? Yes, excellent. It's constant. And how do you know? Because what is the velocity on this graph? It is the fill in the blank of the graph. Velocity is the slope. Good. Slope of this graph. And what's true about the slope of this graph? Well, it's a straight line, so the slope is constant. Yes? Okay. So, this is a qualitative graph. And sometimes when I want to talk about something, I'll use a qualitative graph instead of a quantitative graph. What's quantitative mean?
Numbers.
Lots of numbers. Yeah, there's numbers on it. And now why would I use a qualitative graph instead of a quantitative graph? Because I'm lazy. I don't want to I want to be able to explain something without putting numbers on everything. Okay? I don't need to put numbers on everything. So I'm going to now draw a qualitative velocity versus time graph for this. Velocity and time. And I'm going to put it right underneath it. And what I'm drawing right now is a qualitative kinematic stack. And what a kinematic stack is when I have position versus time and velocity versus time, and eventually down here, guess what we're going to get to? Do you know what's going to be next after velocity? Have you heard of this thing called acceleration, right? Pretend like you didn't even hear that. We're going to do that next week. We're going to get to acceleration next week. Yeah, that'll be exciting. We'll just be, but we're going to do, so now, I want to draw the qualitative velocity of this. So let's take a look at this graph, and what do we know about the slope? Is it positive or negative? Positive. It's positive. Now, we have an idea of steepness, right? It's kind of medium steepness, but we don't really have any idea. We just need to draw a velocity that is positive on my velocity versus time graph. And so I'm going to say, well, the velocity at time t equals 0 is this amount, whatever this slope is. Now, if you were doing qualitative, you would go, okay, delta x over delta t. You would get some kind of slope from that. And this would be my velocity. But no matter what 2 points you picked on this graph, the ratio of delta x over delta t will be the same. It has a constant slope, yes? Okay? Which means the velocity is constant everywhere. Which means that if I say, let's say I just choose that point to be the velocity, well, notice that no matter where I pick for time, let's look at this time, well, the velocity is the same. The velocity is the same at this time. The velocity is the same at this time. So the velocity is a constant with time. Okay? When you say something is a constant with time and you graph it, it's a pretty boring graph. It's just a horizontal line, right? Because the slope here is the same as the slope here, is the same as the slope here, is the same as the slope here. So remember that velocity is, we define average velocity as being the slope of this line. And now I just drew another graph of the slope of this graph. This graph, this velocity versus time graph, is just graphing the slope of this graph. Does anybody know? So what we call a function that describes the slope of another function. Does anybody know what that's called? A function that describes the slope of another function. Have any of you had, well, what do you think? It's called a derivative. Welcome to calculus. I just did calculus. I had position versus time, graph, constant slope. I graphed the slope. It's a constant with time. Okay, that's a derivative. When you take calculus, for the, some of you are going to be taking calculus the first time this year or next year, depending on what math class you're in. That's what a derivative is. It's a function that describes the slope of another function. Now, it's a little bit more complicated than that. If I describe it that way, some of your math teachers might have a little problem with that, but it's good enough for physics, okay? Physics-y definition of what a derivative is. Okay. Now, qualitatively, I could draw a, well, let's just practice a little bit. I'm going to give you a couple of graphs here. Position as a function of time. Position as a function of time. And then we'll do 3 of them. Position as a function of time. And what I want you to do is right underneath it, draw the velocity versus time graph for it. And so we're going to do this. I'm going to start here. I'm going to start on the negative side. So I'm going to do that. Now I'm going to do this when I draw my velocity versus time graph. Okay, I'm going to do this. That is, I'm not going to make it, sometimes the velocities might be negative. So watch for that. Now this one, I'm going to start up here. I'm going to go down like this. So draw the velocity versus time graph for this. Now here's what we mean by side. Do you see how they're lined up? here's my position versus time graph, but then I come down and the velocity axis is just lined up with the position axis, one on top of the other, and time are parallel to each other like that. Okay, so we have this, and then I'm going to get tricky. This will blow your mind maybe. We're going to go up like this, and then we're going to do this. Okay, so draw that. Now take a minute, and I want you to draw very quickly the velocity versus time sketches underneath this. And I want you to think about it now. This velocity versus time tells you what's going on with the slope of this. Wants to know what's going on with the slope. Does it care where the starting position was? No. And on this one, think about the slope. Here, my position was, my object was moving along the x-axis in a positive direction. But on this, as time goes by, the object is moving in a negative direction. And in this one, the object seems to be moving in a positive direction, right? It's moving from here and it goes up here. But then what happens right here? Well, as time goes by, what's happening to my position? Seems to be staying in the same place. So there was a change. And when we draw a kinematic stack, we can show that change like this. I mean, we want the change to take the same place. Okay. Well, now let's go over it. You should have your guesses, your first guess done here. Here, look, it's the rise over the run. Even though my position is on the negative side, my change in position here is positive. So my velocity is positive and the same, and it's constant. So this doesn't look any different than the first example I did. The velocity is a positive, constant value. Is that what you got? Nice. So you weren't fooled by this. That's good. Now, if you were fooled by it, it's okay. We all get fooled once in a while. But just because the position is negative doesn't mean my velocity is negative. Now I look over here and I say, whoa, okay, let's see. If I have a run, what's my rise? Oh, my rise is in this direction. That's a good way to do it. As I go over in time on this one, I go in this direction. I go in the upward positive x direction. But in this one, as I go over in time, I go down. I'm going in the negative x direction, which means my velocity is negative. And notice it's a straight line, so it's constant. Okay? Now, we don't know what this value is. If I put numbers on here, you can figure it out, though, right? Now, this one might be a little tricky. Here I've got a constant slope, constant positive slope. That is, as I go up like this, it goes up. So that means from here to here, I've got this, right? But what happens right here? As I go this way, I don't go up or down at all. I have no delta x, which means my delta x is 0. From point to point here, if I pick any 2 points, here and here, maybe delta t is to the right, but my delta x is 0, and 0 divided by any delta t is 0. So what's true about my velocity? 0. So I just kind of darken it in like that. And some people say, do I need to connect this? You can if you want. And by the way, this sharp corner right here, that little sharp corner, does not exist in nature. You cannot, let's say you run, let's say you're running, and you're running at 3 meters per second. It's kind of a jog. You're jogging at 3 meters per second for a few seconds, and then all of a sudden, you instantly stop. That's going to hurt. If this is a sharp corner, that means you've just run into a brick wall. And even then, if you were to examine it carefully over time, your body, as it crushes against the wall, it would actually take time for it to slow down to a stop. Your head might be a different shape, but it will take time for the mass of your body to come to a stop. So these little corners in real life are rounded, and we're going to talk about that rate of change of velocity here next week when we talk about acceleration. But we're not talking about acceleration yet. So these are kinematic stacks. You have position as a function of time. You draw one on top of the other, and you talk of, and then on the worksheet, I'm going to give you some kinematic stacks, or I'm going to give you position versus time graphs, and I'm going to expect you to draw the velocity versus time graphs. And they're going to be, some of them are going to be qualitative like this. But some of them are going to be quantitative. So, let me show you a quantitative problem. Here's a quantitative type problem. Okay, suppose I give you this equation. So I'm going to write given. And I'm going to say x equals 1.5 meters per second times time plus 1 meter. So that's going to be given to you. I'm going to give you an equation like this. Now, in the textbook or on a worksheet, it might say, an object is moving with the mathematical model given to be x equals 1.5 meters per second times time plus 1 meter. Do you have to write all of that down? No, you can use what I call given, find, and solve. Given, you're given this. Find, I want you to draw a position versus time and velocity versus time for 5 seconds for t equals 0 to 5 seconds. So now they might say all that in words, but if you write it like this, it's a lot faster. You don't have to copy down the whole problem. And by the way, sometimes it's appropriate to use given, find, and solve. Other times it isn't. Okay. I might ask for other things, but I think for this example, this will be good enough. So let's solve it. Well, I want to draw this as a graph, and I want to draw position versus time and velocity, and I want to draw them as a kinematic stack. Okay, I would like all your graphs to be kinematic stacks. So let's draw position as a function of time. But this is going to be in meters, and this is going to be in seconds. Now, usually I do my horizontal axis first, 0 to 5. So I look at how much space I have, 1, 2, 3, 4, 5. And then, now I want to see, I want to scale the vertical axis. So, well, what do I know? I mean, what's the biggest this graph is ever going to get? What's the biggest position I'm going to get? We'll take my maximum time and plug it in, see what I get. Well, what's 5 times 1.5? 7.5? You can get a calculator if you don't believe it. Plus 1 is what? 8.5. So I'm probably going to make this like from 1 to 9 or 1 to 10, something like that. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Then I'll just go 2, 4, 6, 8. Now I'm going to show you a shortcut here. You'll like this. I know what the initial position is. It's 1. At t equals 0, if you plug in 0 here, this term goes away. 1.5 meters per second times 0 is 0. Anything times 0 is 0. And 0 plus 1 is 1 meter. So at time t equals 0, my position is 1 meter. Now, do I have to plug in every time? Well, you can, but you don't have to. Because I know that this is a linear graph. So watch this. This is cool. Plug in 5 seconds. So 1.5 times 5 is, well, 1 times 5 is 5, and then half of 5 is 2.5. 2.5 plus 5 is 7.5, right? 7.5 plus 1 is 8.5. So here's 8, here's 9. So here's 8.5. So there's that. And I know that this is a straight line. So I'm going to connect the dots. Let's see, let's do this. Is this cheating? Yeah, this is cheating. Well, not really. Well, and by the way, if you're wondering, does this really work? Okay, well, put in a different time. Put in 2 seconds. What is 2 times 1.5? 3. What is 3 plus 1? 4. So at 2 seconds, it should be 4. Oh, yeah. It works every time. Yeah, get it? It works. So yes, thank you. Thank you, Luke. That's very kind of you. All right. So you put in any time in here, and you can, check, put in 4 seconds. 1.5 times 4 is 6. 6 plus 1 is 7. So if I go up here, and I should go straight across to 7. So it really works. These things really are kind of amazing, I think. Now we're going to draw the velocity versus time graph. Well, in this case, it's pretty easy because I gave you the position versus time graph, and you know that the velocity versus time graph is just the slope of this graph. So it's just embedded in there. So all you have to do is this, but this has to be the same. 1, 2, 3, 4, 5. Do you see how these are right underneath each other, like this? When you draw a kinematic stack, it needs to look just like that. 1, 2, 3, 4, 5. And this is time in seconds. And you have to label it. Ooh, and we need to title this X versus T, and this is going to be velocity versus T. Now, we're going to make this 1, 2. 1, 2. This is velocity in meters per second. Why did I go to 2? Because I'm only going up to 1.5. So here's 1.5, and it's just going to be a horizontal line like this. And now I have drawn a kinematic stack that's quantitative. Now you might get a data table with position and time, and you draw that, and then you figure out what the slope is, and you draw the velocity versus time graph. And so on. Now let me ask you this. This anticipates what we're going to do next time, but what if I gave you velocity versus time graph? What if this is what I gave you? Okay, Ryan, pay attention. What if this is what I gave you? Could I draw this graph? You know some stuff, don't you? What does this tell you? This tells you the slope. But what does it not tell you? Yeah, it doesn't give you this. Now going from this graph to this graph in calculus, well, in calculus going from this graph to this graph is called differentiation. But what if I want to go from this graph to this graph? This is called integration. Am I off screen? A little bit, yeah. Now, you don't have to know that for this class. You don't have to know that from here to here is differentiation and from here to here is integration. But if you're in calculus, it'll make it easier to understand what the heck is going on in calculus if you understand physics. Anybody in calculus know, you do that thing that plus C? That's what this is. Because you don't know what this is. So they just put plus something we don't know. Something that's constant that we don't know. That's what the C stands for, is constant. So this has to be, if you're going from the velocity graph to the position graph, you have to be given the starting position, the position when time equals 0. That has to be given to you. Or you have to say, we don't know what it is. And we're going to talk more about that, going from one graph to the next to the next. In fact, later on, we're going to have a third graph down here called acceleration. And there's even a fourth graph. Anybody know what the fourth one is? It's called jerk. We don't deal with jerks in this class. All right. Any questions on what we've done? I think we've answered the essential question, right? What is a kinematic stack? Talk about it being a position versus time and a velocity versus time stacked so that the time axes are identical. Okay. And the x vertical axis is lined up with the velocity vertical axis, so everything looks really nice. A qualitative graph means there's no numbers. But it's certainly okay to do problem with numbers, and you can get a quantitative graph and a position versus time and velocity versus time graph. Okay? Any questions? All right. That is all.